All right, our third speaker in this session is Greg Coombe, 2003?
No, 2006.
Well, close. And he is now at Matterport after having been at Google for a long while. He has brought with him Kai Weigel, whom he stole away from us after I did an internship out there last summer. Interesting facts about Greg. He posed for the picture that's on the shirts. For those of you who were here the first time, you know about the shirts because Mark helped with the design. And his more recent thing that he has done, he is a member of a Brazilian samba group, plays the drums, and they were in the Carnival Parade in San Francisco recently.
Yeah?
Yeah, all right, great, thank you.
Thanks, Mary. So my talk today is practical applications of 3D reconstruction and computer vision. It's one of the two talks on that topic. So this is basically the discussion of what Kai and I have been working on at Matterport. It's a small startup. It's about 3 years old. I joined 2 years ago. Our real goal is to generate millions of 3D models. So in order to do that, there's a couple of things that you need to do. The one, it has to be automatic. Like, there's no way that I could manually go into Maya and generate millions of models. Even if I hired a bunch of people, that would be an overwhelming task. So you need some way to capture, process, and deal with many, many, many high-quality 3D models, interior spaces. High quality, I mentioned, the interesting thing about 3D is that, when you're stitching together images from lots of different viewpoints, you get artifacts. Artifacts are very distracting to the eyes, so when you view 3D models with large artifacts, it doesn't matter if 99% of it is good. Like, that 1% will just make you go, what did you guys do here? And large scale is the other thing that we want to do. We're, I came out of this department. I love VR. I want to be able to walk around large environments and large, interesting things. The small scale things, objects are interesting. I think large scale is a more interesting challenge. Before I go any further, and I just want to show a quick demo of some of what we do. Yes, this is a capture of a large interior space. I'm sorry? Yeah, this is in Silicon Valley, yeah, it turns out. Right. Sure. Yeah. So this was captured with the camera that you see right there. And I'll talk a little bit about that and a little bit about how we manage the system. It's a pretty nice house. We also have a bunch of demos up if you look on our website. So I just wanted to give you a little flavor. Whoops, that wasn't the right one. Okay, so as I mentioned, we're the first step in this process to generate these models. We have to build our own camera. There's not really cameras out there that do this. So we built a camera. It's a professional kind of high-end digital SLR kind of price point. It actually has, if you can see, it has 3 sensors in it. So these are the Connect sensors. So they get RGB and depth. It's mounted on a tripod here, and we have a stepper motor in here. So we can very precisely control the rotation of this, which means that we can do the reprojection to a common center projection on the camera. So we have a small 4-core ARM processor in here with software that we built. And that's how we capture these 360 panoramas, so color and depth at every point. It's about, one spin is about 4 million points. So we take a bunch of these panoramas, we stitch them all together, and then upload it to the cloud, process it, and generate these models. So that's the current pipeline that we're working on. And I'll go into depth about each of those 3 components, and then I'll talk about some of the future projects that we're working on too.
Quick question.
Yes.
Vertical field of view for a single scan?
So each of these sensors, the vertical field of view is about 50 degrees, which is why we have 3 of them. So we get about, with some overlap and stuff, we get about 100, somewhere around 150 degrees-ish. So there's a hole at the, above you and a hole below you. Okay. So, like I mentioned, this is based off the Kinect. So this is it's a pretty interesting device. When it came out, it was really eye-opening, I think, for a lot of people. It's cheap, you can get them $200. It does very, very fast capture. The original API is hacked. I think there was a contest, actually, to hack it right when it came out. But Microsoft, in their wisdom, pretty much embraced this and contributed a lot of the work to the OpenAI standard. And so they really encouraged a lot of developer work on that. But this is not, this is not professional grade. This is a consumer grade product. So this is not, like the beautiful scans that you see from the Delta Sphere and stuff that has really high resolution laser things. This is structured light. The quality of the depth is quite poor. There's a lot of noise. Edges are blobby. It's really, you get a lot of variances between different cameras, and it's indoor only. So it's an IR-based structured light, which means that we can't, when you go out into sunlight, it's drowned out by the ambient IR. So we're working within these, basically within these constraints to try to make a really nice camera. So I'll talk about how we deal with a lot of these problems. So calibration is probably one of the things I didn't even realize was super important when we did it. And anyone who's ever, actually, has anyone actually worked with the Kinect before? Actually played around with it and stuff? Yeah, so calibration is crucial with these devices. Like the variances are surprisingly high. By 2 of them, the same manufacturing lot and stuff. Their factory calibration is poor. You have to recalibrate it yourself. Intrinsics, extrinsics, depth, everything. So we spend a lot of time working on calibration, just trying to get high quality data out of it. And this is the quote from one of the people in our company that I really like. Computer vision is a game of early preparation. Like, if you can calibrate and you can get good quality data, everything else is just so much easier, right? And all the errors on your initial part propagate through and cause you just untold pain later on. So step 0 is calibration. Step 1, during the capture, like I was saying, it's spinning around. We actually, originally we would spin 360, capture color and depth. We actually spin 60 degrees now, capturing depth. Then we stop and do a high dynamic range capture. So this allows us to bracket it, get a very high dynamic range. It also removes motion blur. These particular cameras you can run, I think 640, 480. Frame rate, if you put it up to higher res, like, 1280, 1024, it slows down the frame rate dramatically. And so we can use a higher res, slow frame rate, get a high dynamic range when we stop at these 60 degrees. We reproject as we're going along. I mentioned we reproject to a common center, and we use a tremendous amount of statistical aggregation to reduce the sensor noise. So we see, as we're sweeping around, we're running it at a high frame rate. We see every point a dozen or so times. So we do outlier rejection, standard error, and common statistics. And that gets us a lot closer to where we want to be, instead of just raw frames off the Kinect. So the camera itself has some smarts, but it is mostly just trying to run at a high frame rate. So we offload a lot of the smarts to the iPad app. So the iPad app does kind of job management stuff. It also does windows and mirrors. We have the users manually mark those because those turn out to be very difficult to automatically handle. So you can see right here, this area right in here is exterior, and you can see the spray of the capture that went, this is a top-down view, so you can see the spray of the capture that went out through the windows. So we have users manually mark those, and we can fix that up in the later stages. But the most important thing that we're doing on the iPad is the alignment of the panoramas. And this is what allows you to actually walk through a space and capture all the different pieces. So this is, actually I believe this is Alcatraz. This is one of the unused prison rooms where they have a lot of art shows. So you can see how the photographer walked through the different space and how the panoramas align to each other, and it creates this graph. So the panorama alignment, the way we do that, we do kind of a standard, what you would expect. We look in the images, we look for 2D features, generally scale invariant kind of features like corners and points. We tend to have wide baselines, 2 to 3 meters between different panoramas, so we really need strong features that are visible in all of these. We have a panorama which is kind of nice, so that really helps us out when we use the depth for ICP. We have such a wide capture, ICP tends to not slide along things because you generally have an entire panorama. So ICP turns out to work really well on these panoramas. Sorry. Iterated closest points. So it's, the idea is if you have 2 point clouds and you want to align them together, and this is what this bottom diagram is showing. It's funny, it's kind of a dumb algorithm and it works surprisingly well. So you just look at the 2 point clouds. As long as you start pretty close, you just measure, look up a random point in one point cloud, find the nearest point in the next one, and look at that transform. And you do that for a set number of points, and then you figure out the transform which pulls those two together. And then that's the closest points, and then the iterative part is you do it again. And you do it a lot. Okay. All right, so say you have, I don't know how to really draw this.
They want to see it from me, want to use the white one, sorry.
Okay. All right. Let me see if I can do this. All right, so suppose I'll just do this with a triangle maybe. Suppose I want to align these 2 triangles and they look kind of like, they are the same feature, but slightly off from each other. And this is going to be a trivial case because I don't think I can draw a complicated case. So you pick a random point in this, and then find the closest point in the nearby cloud. And in this case, you would do this. And this is some, in 3D, it's some rotation translation. And you do the same for all these points. And you get a system of equations, and you do a linear fit to this. As long as, like I said, the initial conditions matter a lot for this. So as long as you're pretty close together when you start, it'll snap it right together. It'll also generate random transforms all the time. And also I should say that we do a linear fitting. Rotation is nonlinear, so right away you're doing an approximation, your small angle approximation or whatever. So there's the iteration takes care of a lot of that. You kind of wiggle it closer together and closer together.
Is that expensive to do for millions of points on the iPad?
Yeah, if we did it for millions of points. We don't. Oh, Mark asked if it's expensive to do for millions of points, and it would be. So one of the beauties of the ICP algorithm is you can choose small subsets of it. So you can pick, maybe a dozen points in one, find the nearest points in the other. You can do that fairly quickly, pick another set of sample points. If you have a good initial alignment from the features, and then you use the depth to pull it together, you generally get very high quality alignments. We also do this somewhat roughly. For the most part, we don't need to be millimeter accurate. We don't even have millimeter accuracy off the sensor, but we really want to do this as, like I had on the previous stream, we really want to give a high level overview of the space. We don't necessarily care, you can see like this wall, in the actual reconstructed model, it won't be blobby and noisy, it'll be pretty tight. For this, it's fine if it's a little blobby and noisy. Any other questions about that particular step before I go on to more complicated parts. Yeah.
You mentioned localization.
Oh yeah.
So there's like
I have it, but I didn't mention it. Thank you. I owe you. Relocalization. So the interesting thing when you're going through, when you're going through a space like this, you don't necessarily walk through the space in a linear fashion, and you're not necessarily just aligning against the one you came on. So you have to figure out who you're going to try to align against, and this problem in computer vision is called relocalization. So the idea is you could align against potentially anyone in this entire area. So as a practical example, say you're a real estate photographer, you're scanning a house. You walk down a hallway, you walk into a room. You would like to walk out into the hallway and just keep scanning from there. You don't want to have to scan back out of the room and go down. And so what that means is now when you're looking at image features, you're not just comparing against one panorama. You're actually taking all the image features in this, comparing against an entire global set of image descriptors and key points that you have, and then trying to find the best fit. And you're trying to do this in a fairly limited iOS app that has maybe 500 megs of memory. So that turns out to be one of the big constraints. The CPU is actually quite powerful. Memory is the real constraint on a lot of these mobile devices. Yeah, so.
Just to follow up on that.
Yeah.
Do you also do some of the global alignment after that? So I found this was
I owe you again. This is great. So we do a rough local alignment on the iPad, and then we upload this to the cloud, and that allows us to do a lot more complicated global alignment. So now we can load all these panoramas into memory at once, and we can do higher level processing. Like the most common one when people think of global alignment is loop closure. So this is the case where you walk all the way around an environment and come back. In fact, this was motivated, I should tell the story. We had this photographer in Melbourne who was scanning a jail, and it was the Melbourne jail. It's this beautiful old jail. It's decommissioned now. That's weird, that's the second jail one, huh? Anyways, so it's this beautiful old jail, and he scanned, the whole first floor, went up to the second floor, scanned the whole thing, went up to the third floor, scanned the whole thing, in and out of the, they have little displays in the cells and everything. Came down the back hallway to where he had started, and he was like 5 meters off from where he, and we looked at the model, and it was, it was like this huge ledge. And this case doesn't come up a lot in houses, in small houses, which is one of the models that we've been testing on. So we implemented loop closure. And one of the interesting things about loop closure, and a lot of these different techniques, you can see, I have a diagram right up there of interpenetration constraints. So this is the idea, you have, say, two rooms next to each other. The lever arm that they're on is just through the doorway. So if they rotate slightly, the walls crash into each other and your mesh looks terrible. So we do interpenetration constraints, rectilinear assumptions, so the idea that, if you're in a house, walls are flat, they're 90 degrees from each other, ceilings, floors. So we use a lot of priors like that. And that necessitates a much more complex optimization thing. So we use series. I don't know if anyone here is familiar with that. It's a robust nonlinear optimization package that was written, it was originally written, I think, for the Street View team to do loop closure. But it's great. You don't have to write your own Jacobians. It does auto differentiation for you. It's a fantastic package, very simple to use and very, very powerful. So I highly recommend it if you have these kind of nonlinear least squares type of problems. So once we've done the global alignment, we put it into meshing and texturing. We use a voxelization meshing and texturing, basically propagating the color data onto the mesh. And then the last step, we kind of lump this under what we call semantic processing. So this is the idea of understanding what the model consists of, at a higher level than just triangles and textures. So a simple thing is just segmenting out floors, segmenting out rooms. So you can say, I'm a first floor, second floor, third floor, that kind of stuff. Kitchens versus bathrooms. More complicated, detecting furniture in the mesh. This is a table. I can remove it. I can, clear out everything that's in a room, just leave the walls. I can do path planning. I know what doorways are, that kind of stuff. This is kind of a large project that we've done. We've just made some initial steps towards it. But I think it's a really interesting project. It feeds into a lot of different potential applications. Labeling is one of the things that we have thought about and we haven't been able to tackle yet. Like, okay, I know these sort of objects occur in these rooms, so I'm going to, with this accuracy, say this is a kitchen, that kind of stuff. So, yeah, calculating square footage is big for residential real estate. So yeah, if anyone has any expertise in these areas and is interested in a job at a fast-growing startup, contact me. So there's a couple of different applications that we've been working on. So we wrote a little viewer. So you can just do WebGL viewer. That was kind of the demo that I showed at the beginning. Storytelling is kind of interesting. This is much more annotation centric. So the idea, this is actually the, the Ebenezer Baptist Church where Martin Luther King came up. So you can actually walk through this entire, you can walk up on stage where he preached from. And we're working on building in images and video and audio and stuff to really experience a place that without actually going there. Remodeling, so you can imagine large furnishings, remodeling, warehouse store. Very much interested in this. Their current process that they do, if you start a remodeling project with them, they send a couple people out to your house with the laser lights, they measure everything, write it down, they take it back, an artist mocks up a 3D model of it, and then you come in and you put everything in it. So obviously, by the time they even get to interacting with it, they put in a tremendous expense, and users are, if they leave at that point, it's a huge loss. So this one, it's nice. You come in, you scan. If it's just a kitchen or something, it takes 5-10 minutes. And then they have the model immediately available. They plug it into their system. You can drop in furniture, change the cabinets, paint the walls, change the flooring, all of that. And then click one button, check out, done. So that's their vision. Also as sort of a platform, that's the other thing that I think is really interesting. If you can generate high quality 3D models, there are lots of different things that people can build on top of. And they don't want to go through the expertise of this, they just want to be able to use these models. VR is the other interesting thing, and this is particularly dear to my heart, having come up at UNC here. Kai has a little demo. It's hard to, obviously, I can show a video, right? But it's going to be somewhat less compelling than the actual experience. So we brought along a little Gear VR thing. So the idea is you can load these models in, walk around them, and experience them, immediately. So this is, I think this is kind of interesting. I'm just the whole explosion in HMDs and interest in VR and AR. I think it's just fantastic for people that are interested in 3D. So, so yeah. So, like I said, come talk to us afterwards and we can do that. Right, so I just want to, really quick, in the last 5 minutes, Kai has a demo. So that was our professional 3D camera. Mobile, I think, is the kind of new, oh, I've lost someone's attention. So mobile is, this is our this is our mobile second strategy. It is very interesting. We're starting to see now a lot of OEMs putting 3D sensors into mobile tablets. So what this means is now we have to put our entire pipeline that I spent all that time talking about into a small little tablet device. And so when Kai came out last summer, he and I worked on it, and we've been working on it ever since. So I'm hoping we can get a demo set up to see if you can, so we can actually show it, in person.
this cable.
Okay.
I need the adapter.
Okay. Yeah. Oh.
So this is just a Windows Service Pro 3 tablet, and we've strapped one of our depth cameras in the back in lieu of more professional hardware. And we rigged up a programmer art UI. So just sit still for a second. Yes, the issue would be plugging the camera in. So I have a default model of the place, I have no camera attached. As you'd expect, live demos.
So the question,
Great
while I was
idea.
waiting,
A live demo.
on the image that you had that had the windows on the outside, was there a scan made at each of those green dots?
Yes.
Okay.
Yeah, sorry, that was
Okay, where to stand.
right.
Okay, thank you. Wow.
And there is, this is not a mesh, this is a live point cloud. That way we can do move closure on the fly as we walk around. So we can walk in the building and come back. And so we do, right now we're saving frames about 10 frames a second. We can go faster, but then you get data quantity issues.
Captured Mary's.
Yeah.
Gesticulation.
Exactly. Did well at that. It's our gesticulation engine. We'll have some demos afterwards. Either, I don't know if we might get kicked out of this room, maybe in the lobby or something. So you guys can play around with it and scan things and see what you think. We'll have the Gear VR and you can check that out. And yeah, thanks a lot for your attention.
Hey, Mark, question.
Just real quick, I know mirrors are hard.
Yes.
Have you thought about the artifacts caused by glossy reflections?
Right, so that's the other thing, I didn't mention that. That's the other thing that's actually pretty hard. So we have this joke about black pianos, that we just cannot see black pianos. They're glossy, they're highly reflective, you know. So it's interesting, I showed, I a little bit hand-waved over this point, but there's actually two primary outputs for our algorithm. One is a panorama-based output. So what we do is we project the panoramas, like pixel-accurate panoramas, as long as you're at that center point. And then we project that on the mesh. The other is just the pure mesh view, right? And so the panorama has limited mobility, but it looks great, right? It just looks beautiful. The mesh you can interact with, you can move things around and do, but it has these very visible artifacts. So by doing the panorama view, we can kind of avoid a lot of these artifacts. Well, you'll see them during transitions, but they're less noticeable.
Rick?
So you talked about our optimizations using like the rectilinear assumption that walls and floors are 90 degrees from each other almost all the time. Do you use that knowledge to then go in and decimate the mesh? I mean, so if you're assuming the floor is flat, you can reduce that to two triangles.
Yeah. So we do not. We mainly use rectilinear assumptions for alignment. What happens is, if you get a lot of different points at the looking at the same thing, you generally you want to try to squash them together, but they don't actually in the mesh. They look very lumpy, and you want some of that, like a rug. You actually don't want just flat texture. It looks a little bit strange. So setting those thresholds. The other case that we have is like this blackboard. Based on the noise and the tolerances, we would probably classify that as part of the wall. We would just, slap the wall. That's not actually, you might not actually want that. You might want, the little edges to bump out, and so you get that effect, parallax effect as you go by it.
That'll be real. Well, I guess the edges, but I mean, if you've got a surface that's supposed to be flat and two adjacent triangles are like a tenth of a degree off
Right,
from each other.
right.
That's going to look really bad.
Right, and
actually.
well, you know, where it affects us most actually is in bandwidth. So we have to, you know, with mobile devices, there's limited bandwidth, and you want to download the entire mesh to your phone. All this time that we're spending on triangles and the walls and stuff is not valuable time. So yeah, so that's we don't currently use any rectilinear assumptions in. Okay, let me step back a little bit. So when we use the voxelization, we use marching cubes through the voxel grid. We get a massive, massive number of triangles. And so we decimate that down. And so the decimation does take into account local planarity, but not to the degree that we use in alignment. Yeah, Nick?
And let me say that people who want to go off to another talk, please feel free to. Otherwise, we'll let this go a little bit, and if Mark will answer questions as well, and we can stay. Okay.
You fight it out, I don't.
Actually, I'll tell you something that Rick said.
Okay.
So, I assume you don't do any relighting of the playable mesh. You're just using texture maps that are captured with the HDR.
Right.
And
Correct, we don't do any relighting.
if you do relighting, then all those little,
Yep.
you know, tenth of a degree things, just with small mesh elements, they blow you away. So one of the reasons that things like this look really great is because you're using global illumination.
Yeah, exactly. the real global illumination, yeah. Yeah, exactly. So the projects that we have, you know, so the remodeling projects, they tend to be more this where we actually want to modify the environment, then you have to do relighting.
Yeah.
And that really amplifies the effects of these artifacts.
Yeah.
I'm going to ask you if you see more consumer vacation type applications.
Oh yeah, so that's interesting. Yeah, so and someone's question was, do we see more like consumer vacation kind of applications of this? So it's really interesting. Our founder really sees this as a huge area. I'm not totally sold on it, but the idea of sharing experiences is common across all these social networks. If you can share experiences in 3D and the people have a way to view this, it becomes much more compelling. So it's a little bit hard still to capture an environment like this. So you can imagine like a concert or something where things are far away, the lighting is different, the people are moving. It would be quite a challenge to do that. But you could, like a hotel room, there you're like, hey, check out my hotel room. You can easily do that and capture that, and people could see that. So yeah, so he really believes that this is the thing. It's funny because when we did, so the company went through some venture capital rounds, and the initial Series A, he went around telling the story, and everyone was like, whatever, that'll never happen. And then Facebook bought Oculus for $2 billion. And then he comes back and they're like, yeah, we believed you from the beginning. That was really, yeah, we've always believed in you. VCs.
Since last December, there's this Google Cardboard VR project, and also the very cheap head-mounted display.
Yeah.
Did you see a lot of, I would say, a lot of or huge demand for the 3D reconstruction tools such as?
Yeah, so we actually, so Ming pointed out that the head-mounted displays are becoming very, very cheap and mobile and widely available, and did we see that effect for us? So actually we started a whole business line based on this. So the idea is we'll sideload models. There's no real good way to load models. So we'll sideload models into a Note 4 and then send Gear VR to mail it to you wherever you are. So you can actually kind of walk around a house in VR. So that's become, I mean, it's sort of, I would have not have believed that several years ago, but that's, that's the state of where things are, so it's pretty exciting.
All right. Yes?
How do you handle dynamic objects that people?
So how do we handle dynamic objects? We don't. It is very difficult. We have a lot of, when I was talking about the statistical aggregation, dynamic objects show up as outliers and we just reject the depth from that. The image, the images are somewhat worse because when we do the bracketed capture, if you're moving during that, you'll be exposed in certain images and not in others. So it's quite a noticeable artifact.
That's why we concentrate on homicides.
So that's one way to solve it.
Yeah, that's one way. Yeah, we shoot them.
Could you bring back up, I don't know if you saved it, but when Mary, she was actually in one position when Kai scanned the first time.
Yes, you can actually see his head right in the center. You can see several blurred copies of glasses.
Oh, really?
The same issue there.
Yeah.
But I'm not there, right?
Yeah, you were standing already.
Okay.
The previous model, you were sitting and then you had your hands up.
Yeah.
I wanted to see you.
So Mark, move your hands. Yeah. Do a little dance for us. Okay.
Yeah, I was just looking at that.
I was going to try to restart. UI seems to be locked up.
That one I potentially would have putting in there trying to stay still.
Yeah, Kyle will walk around the software room and everyone just kind
So I
of
can tell you
freezes.
that Kai did not show this demo at the VR conference, which was the last week of March, or next to the last week of March. So you guys have been busy in the last 3 weeks.
Just a short question. Is that the camera, is that just the ordinary Kinect or it's modified?
It is the reference platform the Kinect is built off of. So this is the stock device made by PrimeSense. The Kinect is roughly the same sensor.
It's known as Carmine. It is, PrimeSense was acquired by Apple some time ago, so that's been exciting for us.
I'm asking, imagine doing this model. Imagine building a model as you drive past houses.
I think that you would need, so what would you need in order to build models very quickly? You would need, I think you would need very high quality, very fast cameras, and probably an order of magnitude faster than what we're seeing now. If you expect to get any quality of depth. I mean, we get our depth from aggregating lots and lots of frames together, so that inherently limits the speed at which we can capture.
You imagine putting this on a quadcopter or something?
Yeah.
We have imagined doing this many times.
Yeah. I don't know why drones always come up, but they do.
And are there going to be, I was going to say, are there non-infrared sensors?
Yeah, so this particular sensor, the Kinect, like I said, it's at the end of its life. PrimeSense is not making anymore. There are a whole new crop of sensors that are coming out. They're kind of, there's assisted stereo, which is basically you have two cameras and you have a projector. So you get stereo and you get the structured light from it. So that works outdoors as well as indoors. The time of flight, which is pretty interesting, you can get we've seen some very, very impressive time of flight cameras recently. Then one of the nice things about this is the form factor is very small, so you don't need a baseline. You can just do it in one unit. But time of flight has some inherent problems, multipath problems, and then we have seen some structured light ones that are higher quality, brighter, work in somewhat more outdoors.
And your solution to effective range is just to move and do it again?
Right, that's what we've been doing, yeah. So we calibrate, so generally they claim the effective range of this is like 0.5 meters to 4 meters. We can calibrate out somewhat past that, but not too far past that. So
you're looking at other sensors, you make your own camera, does it make sense for you to look at building your own sensor?
Yeah, that's one of the things we've really talked about. That's a whole nother level of engineering project that I think would be expensive and difficult for a small startup to take on. But it's one of these things, well, you know, and one of the reasons that we like the sensor is we've invested a huge amount of time into trying to figure out how to get high quality data out of it. And so, so we know probably more than PrimeSense knows about it. And so, you know, so yeah, so like we keep saying, well, you know, we could build this, we wouldn't do it this way, we would do it this way. But, you know, that's, boy, I mean, if we were Facebook, we could build our own, you know, routers and clusters and do all this stuff, but we're not.
All right, one last question, and we'll go.
Is there any specific aversion to using video and not using all these fancy sensors, just using a camera that's moving around and building all from that?
Yeah, so we could do this just, there's a number of, in fact, this is a very, very active field in the computer vision community to do MonocularSLAM and, you know, all these really fast reconstruction things. The primary one is density. So we want to be able to get very dense capture. And stereo has a high computational complexity if you want, you know, very dense captures. I would guess computation is the other one. So we would like to do this, you know, we would like to be able to scan and have depth immediately. And it's hard to do that in a SLAM kind of system.
All right, let's thank Greg and Kai again. And I guess we'll work.
Yeah, thank you.
And thank you all for coming.